All right, so we will prove Hölder's and Minkowski's inequalities. Uh, these are not conceptual, actually, inequalities. You have to just come up with a, working idea, and then you realize that some inequality holds, and both the inequality and its proofs are kind of ingenious. Okay, it doesn't go step by step. You just come up with a very nice idea that works, and that's it. And here is the idea for this inequality, Hölder's inequality. You start with this function from a closed interval ab into R, defined by this gadget 1 minus alpha, and here where alpha between 0 and 1 is a fixed real number, is a fixed number. So for example, if alpha is 1 over 2, f of x is just x to the power 1 over 2, in other words, square root of x. Okay, and here both a and b are positive numbers. Okay, yeah. Now we apply, so the ingenuity here is to use this function. Okay, apply the mean value theorem to f. Okay, what was the mean value theorem? It says the following: f of b minus f of a divided by b minus a is equal to f prime c, right, for some c in the open interval ab. Here, what is f prime x? Well, it is just 1 minus alpha x to the power. You decrease the power by 1, so you have this. Therefore, and hence, we get what? So this is f. F of b, which is b to the power 1 minus alpha minus a to the power 1 minus alpha divided by b minus a is equal to f prime, which is 1 minus alpha, and then c to the power minus alpha. But you see, c is between a and b. Therefore, c to the power minus alpha, which is 1 over c to the power alpha, is less than 1 over a to the power alpha. Because a is smaller, so a to the power alpha is smaller. Therefore, their reciprocals, the reciprocal of c to the power alpha is less than the reciprocal of a to the power alpha. So we get this. B to the power 1 minus alpha, a to the power, okay, maybe I write this, b to the power 1 minus alpha minus a to the power 1 minus alpha is 1 minus alpha c to the power minus alpha b minus a, and that is less than 1 minus alpha b minus a, and instead of this I write a to the power minus alpha. Okay, well, if you arrange this, for example, divide by a to the power minus alpha, divide by a to the power minus alpha to get, if you do that, you get what? okay, b to the power 1 minus alpha divided by a to the power minus alpha. Well, actually it means multiply with a to the power alpha. If you multiply with a to the power alpha, you get this. If you multiply with a to the power alpha, you get a, and this is less than 1 minus alpha b minus a, and you multiply with a to the power alpha, so they cancel each other. This is what you get, and from this we get the following. So a to the power alpha b to the power 1 minus alpha is less than, here you get, uh, okay, b times 1 minus alpha, b times 1 minus alpha, and then you have minus a, but there is another minus a here. If you take it to this side, it will get, it will be plus a, so they cancel, and then I have also plus alpha a. So this is what we get. Okay, and this holds for all uh, alpha between 0 and 1 and 0 a b. Okay, well, what if I replace a and b? uh, okay, uh, you see, uh, since a is less than b, I have, okay, now if now a is larger than b and greater than 0, so if I reverse this inequalities, then of course I have this 0 1 over a 1 over b, right? Because b is smaller, therefore 1 over b is smaller, and so as above, this is a smaller number, 1 over a is a smaller number, therefore we have, and thus I can just plug this into here. So 1 over a to the power alpha minus 1 over b to the power 1 minus alpha. So instead of a and b, I write 1 over a and 1 over b, and then I have 1 over b 1 minus alpha plus alpha times 1 over a. And if you just rearrange these, you will get this gadget. Let me just write down a to the power minus alpha, b to the power, uh, no, here I have product, sorry, not minus, b to the power uh, alpha minus 1, right? And then I have uh, alpha times b plus 1 minus alpha times a. Okay, uh, okay. So I just actually, what I did, I multiplied this inequality by AB. Just multiply the above with A times B, nothing else. You just multiply this with A times B. This is what you will get. Uh, Wait a minute. If you multiply with A No, you should get 1 over A. Sorry. Wait a minute. Let me write it this way. Okay, multiply this by A times B to get, if you multiply with A times B, so A times this is just A to the power 1 minus alpha, B to the power 1 minus 1 minus this, so I have this. A times B, so I will get A times 1 minus alpha and then B times alpha. Alright, what I get almost the same thing, but alpha and 1 minus alpha are interchanged. However, you see that this holds for all alpha and beta, and to start with, I could just replace alpha with 1 minus alpha, right? However, you know, these hold, both of them hold for all alpha between 0 and 1, and thus we may replace alpha with 1 minus alpha uh, in the uh, inequality uh, in the red box. So I could just replace alpha and 1 minus alpha here and proceed. Then I would just, get alpha and 1 minus alpha here, which is the same as this one. So the conclusion is hence this inequality a to the power alpha b to the power 1 minus alpha is less than this gadget for all a b positive. It doesn't have to be a is larger than b or b is larger than a, any positive numbers, and any alpha between 0 and 1. Actually, I could allow this 0 by just taking limit, but in that case I have to allow also equality here, right? If I take limit as a goes to 0, then both sides will go to 0. Taking limits, we see that uh, a to the power alpha, this is less than, okay, here I have this, but taking limits, I get this. For all a b non-negative and alpha between 0 and 1. Here I don't take limit, okay? Here I don't take limit, only for AB. Okay. All right, so let's continue. Now, we will proceed as follows. Now, fix some real number larger than 1 and let alpha to be 1 over p, okay? Then 1 minus alpha is 1 over q for some, again, real number larger than 1, right? because alpha is between 0 and 1, right? It is neither 0 nor 1. Therefore, 1 minus alpha is neither 0 or 1. Therefore, it's reciprocal. It is between 0 and 1, but it is not 0 or it is not 1. And therefore, its reciprocal, which is q, has to be larger than 1. So, this p and q are both larger than 1, and 1 over p plus 1 over q is equal to 1. Okay, so I just picked two such numbers, and then I will use the above inequality as follows. So set a to be ci to the power p and b di power to the q. Then the above inequality becomes what? Well, instead of A, I will write this. Instead of B, I will write this. Okay. So this is what we will get. Let me write Ci di, right? Okay. Because I take alpha power, alpha is 1 over q. So 1 over q'd power, sorry, 1 over p'd power of this is just Ci. 1 over q'd power of this is just di. And this is less than what? 1 over p times 1 over p times a, which is ci to the power p, and then 1 over q times, which is 1 minus alpha, 1 minus alpha times b. 1 minus alpha is just q, so b is just di to the power q. And here I take a and b were non-negative numbers. Ci and di are non-negative numbers. Okay. And here, let's say this is true for, let's say, for I from 1 up to k. Okay, I have k many such numbers. They all obey this. Okay, now add them up. Take sum over I to get what? Summation ci di I from 1 up to k will be less than summation I from 1 to k 1 over p times ci to the power p plus 1 over q times di to the power q. Okay. And finally, I will do this. Now, finally, let ci to be this. Some other real number, and then here I have this summation. J from 1 up to k psi j to the power p and 1 over p, and di is this, nu I divided by the same thing, j from 1 to k nu I to the power q 1 over q. Okay, and I'll just plug this into this inequality. Here psi I are just arbitrary real numbers. I take their absolute value, so these are all non-negative. One thing we have to be careful that not all psi i's and nu i's are 0. because if it is the case, then denominator becomes 0. So not all of them are 0, but later we will let them to be 0. Okay. So if I put all this into this, I will get what? You see, the denominator is a common term, right? This doesn't depend on I. It's a fixed term. And here's the same thing. So numerators change by I, right? But denominators doesn't. So when I plug them into this summation, this is what I will get. Plug them into the above inequality to get what? I will get this. Let me write. Psi I, nu I from 1 to k. And I have this common denominators. These are multiplied, so I have this common denominators. Maybe I write it here. The first one and the second one. And this thing is less than what? This thing is less than. Okay. Less than what? You see, 1 over p times pth power of this. When you take pth power of this, you will get, you see, when you take pth power, you will get p here, and this will disappear. You will get p here. I will get qth power of this. So you will get q here, and this will disappear. And when you add these up, when this add these up, you just add actually this, the sum over I will be just the denominator. So sum of ci to the power p's will be just 1. And sum of di to the power q's will be again 1, because the numerators adds up to the denominator. And here again the sum of the numerators will be equal to the denominator. So in the summation, sum of ci to the power p's will be 1. Sum of di to the power q's will be 1. So what is left? 1 over p times 1 plus 1 over q times 1. So what you will get here is this. 1 over p times 1 plus 1 over q times 1. But this is just 1 over p times 1 over p plus 1 over q, but 1 over p plus 1 over q is another 1. So this is what we get, okay? So this times this gadget is less than 1. So if I take this stuff to the other side, we get I from 1 up to k, psi I, nu I is less than this two summations in product form. Here j is a dummy variable. Okay, I can just replace this j by I, doesn't matter. So I'll do that. It's a dummy variable, 1 over p, and then I from 1 to k, nu I q 1 over q. Okay, this is true for all psi I nu I in R, so that actually here they are true, provided that not all psi i's and not all nu i's are 0. However, once you have this, okay, If this is true for all non-zero psi I nu i's, then again taking limit as psi I, some psi I or nu i's goes to 0, it will still hold. But yeah, it will still hold. Therefore, you know, you will have this inequality for all psi I nu I. So there is no harm, you know, letting them arbitrary real numbers. And this inequality is called this is called the Hölder's inequality. Okay, it's a very important inequality, as you will see in a minute. Beni duymadığınız için soruda soramıyorsunuz ama yok, pardon, duyuyorsunuz da ben sizi duymuyorum. Okay. All right. Now, oh yeah, sorry. Okay. Yeah. All right. Now let's consider the other inequality. Minkowski's inequality. This is basically the triangle inequality for you know, the row metric or the p metric. Okay, now consider this, the inequality to the power p. Well, I can write this gadget as like this, p minus 1, okay, p minus 1, and apply triangle inequality to this first term, right? This is less than psi I plus nu I, oops, times this gadget, and if I open this up, you get, I will get this. And then we apply Hölder's inequality to these products. I'll take some summation over I from 1 up to k, and apply Hölder's inequality uh, to the products. So this is what I mean. When you take summation over I, you get this, I from 1 up to k, and I apply Hölder's inequality. So this is like, you know, Xi, and this is like nu I. This will be less than what? This will be less than product of two summations. The first sum is this. I take pth powers of this, 1 over p to power, and then, sorry, k, q to powers of this, q times p minus 1, and then 1 over q here. Okay? Alright. But you see, since 1 over p plus 1 over q is equal to 1, this gadget, so we get p times q. If I multiply both sides by pq, I get p times, no, q times p is equal to pq, and therefore this exponent here, qp minus qp minus q is equal to p. So this thing is just p. Okay. So we get this. Let me write. I from 1 up to k, psi I plus nu I to the power p minus 1 is less than, sorry, I from 1 to k, psi I to the power p 1 over p plus, wait a minute. Yeah, this is plus, right? Not times. No. Yeah. Yeah, no. This is times. Okay. All right. Yeah. Okay, this is p, and then I have 1 over q here. Okay. Yes. So I have what? Wait a minute. Let me check. Yeah. Okay. So we have the following. Hence, uh, this expression here. Okay. Well, this was less than this and this. So I apply to both of them Hölder's inequality, and this is what I will get. This is what I will get. Okay. I have this term from the first one, so less than, let me write it this way, I from 1 up to k, psi I to the power p, and then 1 over p. From the other one, I will get nu I, the same thing with nu I from 1 to k, nu I to the power p, yes, 1 over p, times there's a common term here, I from 1 to k psi I nu I to the power 1 over to the power p and here to the power 1 over q, right? P and then q. So I have the same thing for right. I wrote this for the first term. For the second term, I have the same thing. The only difference is that instead of psi I have nu I here. This term doesn't change. So when you add them up, you get psi I and then nu I and then the common multiplier here. Okay. Well, now I take this term to this side, dividing this. So we get what? I get this. Pth power of this, I from 1 up to k, to the power, this is first power, but when I divide with this, I have to subtract this, right? And this is less than the sum of these two, I from 1 up to k, psi I to the power p, 1 over p, plus nu I to the power p, 1 over p. And 1 minus 1 over q is also 1 over p. Okay. So we get I from 1 up to k, psi I, nu I to the power t, and then 1 over pth power of this is less than I from 1 up to k, psi I to the power p, 1 over p, plus I from 1 up to k, nu I to the power p, 1 over p. Okay. And this is called, so this is true for all psi I, nu I. Okay. Again, we divide by, some stuff. There you have to assume that not all of them are 0. But once you get this, taking limit, you see that you may just take those to be 0. Okay, there is no harm in doing this. This is called Minkowski's inequality. So this thing here. Okay. This is called Minkowski's inequality. All right. What is the use of this? Let me see. Okay. I'm checking the chat box if there's a message from you. Okay, now corollary of this is the following. We have done actually this before, but there we had a special case where all the metric spaces were real numbers with absolute value metric. Now we consider something more general. So let x1 d1 xk dk be metric spaces. Then for any p larger than or equal to 1, okay, larger than 1, let's say, I will use the above stuff for any p. The metric, the function d from x cross x dp, let me say, into r, where x is just the Cartesian product x1 xk, and dp is this. If I have two elements in this product, then I just take summation of the distances pth powers I from 1 up to k, and then take 1 over pth power, where x is just x1 xk and y is y1 yk. So whenever I take two k tuples, uh, the first coordinates are in the first metric space d1. So I look at the distance between these two elements x1 and y1, and then the second coordinates are from the metric space x2. So I look at the distance d2 x2 y2 and add these things, taking pth power, add these things up, and then I take 1 over qt 1 over pth root. Now this function uh, defines a metric on the Cartesian product, okay, xk. The only thing non-trivial in the proof of this corollary is the triangle inequality, to showing the triangle inequality for this metric, and the triangle inequality will follow from Minkowski's inequality. So proof M1 and M2, this trivially holds. For M3, one needs to use the Minkowski's inequality. Okay, and I will leave this to you as an exercise, left as an exercise. It's easy, I mean, just an exercise. And what else? I will write down one more thing, another corollary, actually, let's say proposition. The matrix d1 dp and d infinity are all equivalent, where I didn't tell you what d1 and d infinity are. Actually, we did these where d1 is this, d1 xy. So I'll just take p equals 1 when p is equal to 1. So this is 1, this is 1. So you just add them up, right? d1 is this, summation di xi yi I from 1 up to k, and d infinity. Remember, what was this? This was the maximum of these terms, right? So it is just the maximum of d1 x1 y1 up to dk xk yk. And I claim that all these metrics are equivalent. And the proof of this is done for the special case where, uh, recall that we proved this for uh, xi di to be the real numbers and the absolute value metric. Okay, so di xi yi is just xi minus yi. Okay, before we proved this before for the special case, but the proof is the same. So I will just leave it as an exercise again. I will not prove this. The point of this, what? You see, when you have metric spaces, you can take Cartesian products like this. And then, of course, there comes the question of which metric to be chosen on this product. There are many choices. And these are not actually all the choices. I listed infinity many of them, but there are others. And what we claim is that all these choices, at least the ones I listed here in this proposition, okay, d1, dp, p is any real number greater than 1, and d infinity, all these metrics are equivalent, okay? So that's the result. All right, I think I can stop here.